The Webb, friends, is so far out that finding light has been traveling for in excess of 13 billion years. Anyway, the universe has been growing, and hence, the light has been extending for the most far-off cosmic systems. We are thinking back in time almost to the Big Bang. The vastness of the universe could seem immense, yet every single bit of it began from what we allude to as the peculiarity. At this point, this is the way we interpret the Big Bang theory. However, the James Webb Space Telescope, JWST, has revealed critical secrets about the birth and development of the universe, leaving us confounded. Famous physicist Brian Cox has broadcasted that the striking discoveries made by the JWST could truly reshape our perception of the universe in general. Join us as we dive into these new celestial revelations that promise to disrupt our understanding. The James Webb Space Telescope, named after the recognized NASA administrator James E. Webb, stands as a miracle in current cosmic research. This telescope represents a huge technological leap forward from its precursor, the Hubble Space Telescope. Happening as a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST outperforms the capabilities of its predecessor. It uses cutting-edge technology and a design optimized for studying the universe in surprising detail. Unlike the Hubble, the JWST provides clear and sharp images of distant celestial bodies, primarily operating in the infrared spectrum. This unique feature allows it to penetrate cosmic dust and capture divine objects that were previously hidden from our view. With its colossal 6.5-meter primary mirror, made from 18 hexagonal segments, the JWST dwarfs the Hubble's mirror in size. Positioned approximately 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in a balanced state with Earth, ensuring a steady and continuous view of the universe while exploring distant corners of space. Investigating light years away also involves a form of time travel. The JWST utilizes infrared instruments to observe celestial objects and events, going back billions of years. The light emitted by these objects, due to the expanding universe, undergoes a redshift, shifting from the visible range to the infrared range or longer wavelengths. Fortunately, the JWST can detect this infrared light emitted by celestial bodies at extreme distances, enabling scientists to study star formation, galaxy development, and exoplanet atmospheres. Its latest prominent discovery includes identifying a massive cluster of galaxies at the edge of the observable universe. This finding challenges the validity of the Big Bang theory, prompting a reassessment of our fundamental cosmological assumptions. To better understand how we got here, we must take a brief journey through the history of space exploration. Early civilizations like the Greeks and Chinese laid the groundwork for understanding planetary motion by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, a pivotal space expert, made groundbreaking discoveries in cosmology and observational space science. His observations revealed that distant nebulae were separate galaxies, far beyond the Milky Way, transforming our understanding of the universe's size and expansion. Hubble's law, formulated by him, showed that galaxies farther away were receding at higher speeds, providing evidence for the expansion of the universe. The post-World War II era marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital flight in 1961, and the Apollo 11 moon landing in 1969 as milestone accomplishments. Fast forward to 1990, when the Hubble Space Telescope was launched, providing unprecedented clarity and astonishing insights into the universe. The journey from ancient observations to the technological marvels of the James Webb Space Telescope highlights the continuous evolution of our understanding of the universe. It revealed the immensity of space and reshaped fundamental ideas in astronomy. Take the Hubble Space Telescope, HST, for example. It captured the famous Pillars of Creation image in the Eagle Nebula, revealing a stellar nursery formed by massive columns of gas and dust. Another key achievement was the Hubble Deep Field, which captured thousands of galaxies in what seemed to be an empty patch of space. The HST also studied exoplanet atmospheres, identifying elements like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Following the discovery of the closest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These achievements established the Hubble Space Telescope's legacy as a foundation of modern space science, captivating the world with its stunning astronomical revelations. Its successor, the James Webb Space Telescope, JWST, was launched to build upon technological advancements and lessons learned from Hubble. One example is how we now understand the universe's origins, explained by the prevailing Big Bang theory, which states that around 13.8 billion years ago, the universe began as a hot and dense singularity, rapidly expanding, resulting in matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the structures we observe today. The Big Bang theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted, the theory faced skepticism and challenges in its early years. Alternative models, such as the steady-state theory, proposed a universe without a distinct beginning, and concerns arose about evidence supporting the initial singularity, the expansion component, and observed anomalies. Many of these issues were addressed over time, with a key piece of evidence coming with the discovery of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, along with technological advancements, also supported the theory. Precise measurements of cosmic microwave background radiation matched theoretical predictions remarkably well. Enter the James Webb Space Telescope, equipped with advanced infrared instruments capable of peering through cosmic dust clouds, operating primarily in the infrared range. The JWST captures the oldest light in the universe, observing objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on star-forming regions, stellar nurseries, and the birth of stars, which are obscured from optical telescopes. Infrared light, with longer wavelengths than visible light, penetrates interstellar dust clouds, overcoming a limitation of the Hubble Space Telescope. The JWST can detect cooler objects emitting primarily in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light stretches, causing a redshift. The JWST's infrared capabilities detect these redshifted signals, capturing light from the early universe and offering insights into its growth and evolution. Events like black hole formations or new starbirths, which predominantly emit in the infrared range, further enhance JWST's observational abilities. The telescope can investigate phenomena that would otherwise be hidden or imperceptible. The JWST complements optical telescopes like Hubble by offering enhanced sensitivity and the ability to detect infrared radiation. This ability allows it to peer deeper into space and delve further into cosmic history, uncovering hidden celestial wonders and offering a broader perspective on the universe's development. The JWST serves as our window into the earlier stages of cosmic evolution. Recently, it uncovered something so astounding that it could provoke a reconsideration of the entire cosmological model of the universe. We've found massive clusters of galaxies at the very edge of the observable universe. These ancient galaxies existed only a few 100 million years after the Big Bang, marking the cosmic dawn. The amazing part is that we're uncertain how such massive structures formed so early in the universe's history. This disclosure might lead us to re-examine how we might interpret the arrangement and development of worlds in the early universe. Concentrating on early universes is pivotal for disentangling the secrets of vast starting points. The JWST can give insights into how systems, stars, and planetary frameworks arose and advanced over billions of years. These perceptions also add to broader inquiries about the key nature of the universe, including its composition, structure, and the forces governing its development. While the Hubble Space Telescope was groundbreaking for its time, it had limits in observing the early universe. Its primary limitation was its failure to effectively penetrate cosmic dust and detect the infrared light emitted by old galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe, where these frequencies are absorbed or distorted by cosmic dust and gas. The James Webb Space Telescope represents a remarkable leap in observing galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered a wealth of ancient galaxies, offering extraordinary clarity and detail in understanding the universe's transformative history. Starting discoveries from JWST observations have caused waves and established published cosmological models with detailed data, testing several aspects of prevailing theories. Cosmologists are rethinking core principles governing how we interpret cosmic development and structure. Disparities between observed data and theoretical predictions have sparked intense debates among mainstream researchers. JWST observations have revealed more galaxies in the early universe than anticipated by existing models, suggesting a more complex and rapid development process. Some observed early galaxies appear more evolved than predicted, challenging traditional models that anticipated slower evolution. The discovery of an enormous mass of galaxies challenges the assumed distribution and arrangement of large-scale structures, unveiling a more intricate and denser cosmic web than previously thought. These observations raise intriguing questions and avenues for further investigation. The presence of massive structures challenges early models of large-scale structure formation, prompting researchers to refine models for a better explanation. Understanding how such enormous structures assembled quickly after the Big Bang presents a puzzle that requires an explanation that doesn't violate key principles of cosmology. Significant discrepancies in the conditions of the early universe, compared to predictions based on existing models, have also been revealed. These differences may suggest previously unknown physical processes, unexpected circumstances, or unidentified galactic phenomena. Simply put, these variations have prompted scientists to re-examine and improve our models of the universe. Right now, all we can say is that further investigation is required to integrate these remarkable observations into a more comprehensive understanding of the universe's origins. Observations often provide exciting glimpses into the universe, but in-depth analysis sometimes uncovers errors. For instance, early observations could suggest specific properties or features within distant galaxies that, upon further investigation, reveal differences in their formation, structure, or evolutionary pathways. In simple terms, cosmic phenomena are extremely complex and require careful scrutiny for us to truly understand their true nature. Spectroscopy, a method that unravels the properties and history of celestial objects, is one example. It involves analyzing the light emitted or absorbed by celestial bodies by studying the properties of the light. Spectroscopy provides detailed information about the chemical composition, temperature, density, and motion of celestial bodies. This study helps us understand the origins, evolution, and contributions of celestial objects to the cosmic tapestry. The JWST has uncovered several instances where initial observations differed from later analysis. For example, early observations of distant galaxies suggested a basic composition predominantly dominated by light elements like hydrogen and helium, in line with theoretical assumptions. However, spectroscopic analysis using the JWST revealed intriguing variations in key markers, identifying heavier elements or compounds previously undetected or misinterpreted in the early universe. This challenges conventional ideas about the early universe's chemical composition and the processes responsible for their formation and distribution across cosmic distances. Furthermore, initial assumptions about galaxies in the early universe were based on basic observations suggesting a relatively uniform pattern of growth and organization. However, more extensive studies by the JWST uncovered a much more diverse and complex range of elemental arrangements within these galaxies. These differences have reshaped how we understand evolutionary pathways, suggesting that the forces governing the structure and development of galaxies in the early universe may be far more intricate than previously suspected. On the other hand, the JWST has also confirmed some earlier hypotheses and observations. For example, spectroscopic measurements by the JWST confirmed the presence of hydrogen, helium, carbon, oxygen, and nitrogen within celestial objects, supporting theoretical predictions. These findings align with the widely accepted lambda cold dark matter model, which suggests the universe began with a Big Bang and consists of ordinary matter, and dark energy. However, since some predictions of this model have been tested by later JWST discoveries, alternative possibilities, such as the cold dark matter model, which suggests most of the universe's matter is dark matter, are being considered. This elusive matter, unlike visible atoms, doesn't interact with electromagnetic forces but exerts a gravitational impact. The model aligns with our understanding of cosmic microwave background radiation on a large cosmic scale, though challenges arise at smaller scales, where inconsistencies exist in the model's predictions regarding the internal structure of galaxies and the abundance of small satellite galaxies around larger ones. Another proposition is the semi-consistent state cosmology, which suggests the universe follows a repeating pattern of continuous expansion and contraction, challenging the Big Bang singularity. This model remains speculative due to its deviation from conventional models and the lack of direct observational evidence supporting its repetitive nature. The mirror universe theory proposes the existence of an identical parallel universe running alongside our observable universe. This model suggests the mirror universe may have its own physical laws and particles, offering an alternative explanation for various cosmic mysteries. However, it lacks observational proof or experimental data and remains largely speculative. The digital recreation theory suggests our universe could be a sophisticated simulation. Proponents argue that our reality might be a highly advanced simulation, similar to virtual reality. This idea stems from philosophical considerations and faces challenges in providing observational confirmation or disproof. Lastly, the multiverse theory proposes the existence of multiple universes, each with its own set of physical laws and properties. Our universe is merely one among an infinite number of universes, each with different constants and possibly dimensions. While fascinating, we cannot directly observe or access other universes, making it speculative. While alternative cosmological theories may not be as widely accepted as the lambda cold dark matter model, it's important to remember that even the latter faces skepticism from the outset. Confirming or disproving these speculative theories is challenging, but they may warrant consideration if our current cosmological model falters over time. Ongoing discoveries, though informative, have not disproven the theory of primordial cosmic inflation. According to many experts, observations from the James Webb Space Telescope have enhanced our understanding of cosmic history, aligning with Big Bang predictions. Massive galaxy clusters at the farthest reaches of the observable universe suggest gravitational forces were at work even in the early universe, in accordance with the Big Bang's expectations. The presence of these massive structures at the edge of the observable universe implies their light has taken billions of years to reach us, offering a glimpse into the universe's past and supporting the theory's predictions about evolution. However, these observations also present anomalies, challenging established scientific examination. The JWST has opened new vistas, allowing us to explore the ancient domains of the universe. With the JWST, we face a cosmological landscape filled with new questions and intriguing possibilities. These uncertainties challenge established cosmological principles, prompting a reassessment of how we interpret the universe's birth, evolution, and key laws. Considering such revelations, it's important to remain open to rethinking our cosmic narratives. These new discoveries are, however, only the beginning of the ongoing journey of cosmic exploration, urging us to continue our pursuit of cosmic insights through further research and continuous advancement in the field of cosmology.